Hello and welcome to the final demo presentation for Beat Laser, an interactive music rhythm game created for ECU 4960 Integrated System Design 2. For our final senior design project, our team wanted to create a device that demonstrated and expanded our engineering and project design skills in a novel but impactful manner. Multiple members of our team are musicians or music lovers, so we decided to develop a device that has musical applications. To make the device more approachable to a wider population, however, particularly to non-musicians, we set out to create an interactive music game that would not require any existing musical skill, similar to popular rhythm dance games or Guitar Hero. To create an engaging audiovisual experience, we decided to create a laser harp with built-in audio playback and an LED-based game display. Pictured here is the design sketch for our final prototype. The laser harp module consists of 8 laser beams that are projected from a central beam and a stepper motor that can be interacted with by the player to play notes similar to a traditional harp. The game display board is built from 8 LED strips that mirror the 8 laser beams with an LED that is animated to drop down from top to bottom to indicate when notes should be played along with audio feedback. The game display board also includes a small display that shows the player's score and allows for song selection.
Beat Laser's motor laser system is what is responsible for creating the illusion that a single laser beam appears as multiple. The infrastructure contained in this system includes a NEMA 17 12-volt 350 milliamp stepper motor, a TMC2208 motor driver, and a 12-volt 50 milliwatt laser. In order to create this illusion, a small mirror is attached to the shaft of the stepper motor. The position of the shaft of the motor controls whether or not the laser is on or off. When the shaft is in the correct position, the laser will be pulsed. The number of times the laser pulses depends upon the desired number of beams. Since the shaft is moving so fast, it appears that each of the beams created appear continuous. But in reality, they are not. They are only being cut on and off at the desired times. The stepper motor is controlled by 2 inputs sent from the Raspberry Pi. These 2 inputs are the direction that the shaft needs to turn, as well as the time that the shaft needs to take a step. The micro-stepping operation deemed most suitable for this project is quarter-stepping. In quarter-stepping operation, the shaft is moving fast enough to maintain the illusion of continuity in the laser beams, as well as creates the smallest amount of vibration seen in the motor. When the motor is moving faster than quarter stepping, the beams appear to be scattered and not in the same direction. The motor driver being used is the TMC2208. The 2 pins MS1 and MS2 are used to control the size of steps of the shaft of the motor. When MS1 is tied to ground and MS2 is tied to positive voltage, the motor is in quarter stepping operation. Since the enable pin is reverse logic, the motor driver's enable pin is directly tied to ground so that output is always available.
The next major component of the Beat Laser project is the LED display board. It was composed of 8 LED strips that were soldered together. Each LED strip corresponded with a particular laser beam. During the game, an LED at the top of the board would light up and descend downward. Once the LED at the bottom was lit up, it indicated to the player that they should break the corresponding laser beam. The input pins of the LED strips consisted of a 5-volt source, a ground, and a data pin. In order to operate the LED strips, a level shifter was implemented. This was necessary because the 3.3 output of the Raspberry Pi was incompatible with the NeoPixel data pin. With the level shifter implemented, the Pi could then light up the LED strips using a PCM signal.
The LDR, or light-dependent resistor circuit, is a critical component in the Beat Laser design. The LDR circuit indicates to the Raspberry Pi when one of the 8 laser beams is broken by the player. Because the Pi only has digital I/O, This is accomplished by switching the voltage on an input pin on the Pi between 3.3 and 0 volts using a 2N7000 MOSFET. The behavior of the FET is controlled by a voltage divider on its gate, composed of 2 resistors, a potentiometer, and a photoresistor that decreases in resistance when exposed to light. These components are arranged in a voltage divider configuration on the gate of the transistor. When a laser beam is cut by the player's hand or the paddle, the reflected light incident on the photoresistor causes a drop in voltage at the gate of the transistor, placing the MOSFET into cutoff. As a result, the voltage on the drain will be approximately 3.3 volts as supplied by the Pi's 3.3 supply. This voltage, or any above 1.8 volts according to the Pi's specifications, is interpreted as a digital logic high. Conversely, when the light is not incident on the photoresistor, the voltage at the transistor's gate places it into saturation, causing the voltage at the drain to go to 0 and the Pi to read a logic low. This circuit can be tuned to the ambient light present in a room using the potentiometer, adding some robustness to the sensor's design. The amplifier and audio playback module for Beat Laser is fairly simple. Although the Raspberry Pi supports analog audio output through its 3.5mm audio jack, it does not provide sufficient power for audio playback through speakers without additional amplification. As a result, Beat Laser relies on the MAX 9744 Class D 20-watt amplifier to power 2 8-ohm 1-watt speakers that provide the audio cues for the game. The amplifier is powered by the device-wide 12-volt bus and receives a stereo, unbalanced analog signal from the Raspberry Pi. During testing, our team encountered errors with the Raspberry Pi's onboard audio output and DAC, so a small USB sound card with a separate 3.5mm output jack was used to convert the digital audio from the Pi to an analog signal that could be amplified by the board. The software for Beat Laser, designed in Python, is built around the MIDI data standard, which stands for Musical Instrument Digital Interface. We used the MIDO Python library in order to process and work with the MIDI data, and we read in selected MIDI files as the original song and processed the data in order to be able to have visual playback and audio cues for the players. The song is played through the speakers using the Pygame module, which converts the MIDI data notes into audible signals. The program signals when LEDs on the display should start to trickle down on one of the 8 strips specified by the program, corresponding to when notes should be played by the player. The program also then takes the digital input provided by the LDR circuit and turns that into MIDI data that can be compared against the original song to provide a score to the player on their performance.
When we first began to make our subsystems run simultaneously, we began by running everything within threads. However, this caused general slowdowns within the subsystems. Because only one processor was being used, it would constantly switch between the subsystems, causing significant slowdowns, in particular with the LEDs and the motor. To fix this, we decided to switch from using solely threading to a hybrid approach with both threading and processes. In our final prototype, we take advantage of our multi-core processor, and each subsystem runs on its own process. Within the MIDI process, which plays the song and keeps score, it'll send a message to the LED board to indicate that a pulse needs to go down at that moment. Each indication will spawn a thread directing the LEDs to create said pulse. Once we've figured that out, the flow goes as follows. Once the program is started, the initial GUI will pop up, and the motor process will begin to show 3 laser beams. Additionally, 2 event handlers are set, one of which is for the LDR and the other for song selection. Once the song is decided on and that event triggers, the program will destroy the current GUI and kill and rehome the motor process. Once that's done, it will start a new motor process with all 8 beams and begin the MIDI process. This process will 1. Play the selected song, and 2. Spawn the LED threads that correspond to it. Once all of that is done and the song is done playing, the program will output your final score.
The lasers will allow for a UI selection of the song that the user decides to play. The motor will create 3 laser beams to correspond to left, right, and center to select. Once the song is selected, that information will be sent to a file to start the game. This information includes the MIDI file, the associated channel number, and the pace. The timing of the LEDs is synced up with the MIDI data to be exactly 1 second before the note hits. So this means that the LEDs will start to come down one of the designated strips from the top of the board to the bottom within 1 second, so that the user will then know that they have to interrupt the laser that corresponds to that specific strip at that time. We had to make some adjustments to the pace at which the LED falls, which is unique to each of the songs. The motor will then create 8 lasers once the song is selected, which correspond to each of the 8 LED strips. The LED will trickle down the board as a warning to the user that the corresponding laser should be interrupted soon. This will be signaled using the LDR. The ideal time and corresponding laser are stored in an array, which is compared to the user's results. This compares the data and provides the user with an accuracy output score.
On the left, you can see our final prototype all put together. In the back, you can see the LED board with the 8 LED strips, and in the front, you can see the container holding the bulk of our project, which includes the Raspberry Pi, motor, laser, LDR, and amplifiers. And on the right, you can see the 8 laser beams clearly visible, all originating from one laser and a stepper motor. And finally, here is our project in action.
In conclusion, all the stated project goals and deliverables were met. The game can be played with little to no interruption, the laser beams are used to control the system, and players receive a final score after they complete a game. If more time was available, finding a stronger computer with more memory and cores that would replace the Raspberry Pi would be a top priority. That being said, the project was still a great success. Our team was able to utilize various software, computer, and electrical engineering practices and principles to get this project completed before the deadline.